My name is Paul Moore, and I will be speaking about the physics of catapults. Catapult physics is basically the use of stored energy to hurl a projectile without the use of an explosive. The three primary energy storage mechanisms are tension, torsion, and gravity. The catapult has proven to be a very effective weapon during ancient times, capable of inflicting great damage. The main types of catapults used were the trebuchet, mangonel, and ballista. These siege engines were used to destroy enemy walls or fling projectiles over those walls. Among the various types of catapults, the trebuchet was the most accurate and among the most efficient in terms of transferring the stored energy to the projectile. In addition, it allowed greater consistency in the throws due to the fact that the same amount of energy could be delivered every time, by way of a raised counterweight. A trebuchet works using the energy of a falling counterweight to launch a projectile using mechanical advantage to achieve a high launch speed. For maximum launch speed, the counterweight must be heavier than the projectile. The counterweight pivots around a much shorter distance than the projectile end. The advantage of this is that the projectile end of the beam reaches a much higher linear velocity than the counterweight end of the beam. This is the principle of mechanical advantage, and is what allows the projectile to reach a high launch velocity. However, because the counterweight pivots around a much shorter distance, its weight must be much greater than the weight of the projectile to get a high launch velocity. The sling releases when a certain angle is reached. At this point, the ring slips off and the projectile is launched. The release angle can be adjusted by changing the finger angle. As the beam rotates counterclockwise, the projectile experiences centripetal action, which causes it to move outwards. This results in a large increase in linear velocity of the projectile, which far exceeds that of the end of the beam to which the sling is attached. This is the heart of the physics behind a trebuchet, and is the reason why a trebuchet has such great launching power. The mangonel is what people are most familiar with when they think of catapults. The mangonel consists of an arm with a bowl-shaped bucket attached to the end. In this bucket, a projectile is placed. Upon release, the arm rotates at a high speed and throws the payload out of the bucket, towards the target. The launch velocity of the payload is equal to the velocity of the arm at the bucket end. The launch angle of the payload is controlled by stopping the arm using a crossbar. This crossbar is positioned so as to stop the arm at the desired angle, which results in the payload being launched out of the bucket at the desired launch angle. The mangonel was best suited for launching projectiles at lower angles to the horizontal, which was useful for destroying walls, as opposed to the trebuchet, which was well suited for launching projectiles over walls. However, the mangonel is not as energy efficient as the trebuchet, for the main reason that the arm reaches a high speed during the launch. This means that a large percentage of the stored energy goes into accelerating the arm, which is energy wasted. This is unavoidable, however, since the payload can only be launched at high speed if the arm is rotating at a high speed. So the only way to waste as little energy as possible is to make the arm and bucket as light as possible, while still being strong enough to resist the forces experienced during launch. The physics behind the mangonel is basically the use of an energy storage mechanism to rotate the arm. Unlike a trebuchet, this mechanism is more direct. It consists of either a tension device or a torsion device, which is directly connected to the arm. The fact that a mangonel uses an energy storage device that consists of a deforming material, like wood or rope, means that its throwing distance will not be as consistent as the trebuchet. This is because these materials naturally wear and lose elasticity during their use. This is something that needs to be constantly monitored during a battle, with replacement materials made readily available if necessary. The ballista is similar in principle to a crossbow, but much larger. Like the torsion-powered mangonel, it used twisted rope as the energy source. The picture on this slide shows the torsion mechanism consisting of twisted rope, located at the pivot location of the two sidearms. In the ballista, the bowstring would be winched back and the tension set. It would be used to launch darts, bolts, and spears with deadly force and accuracy. It could also be used to launch stone projectiles of various sizes. Thank you for watching. I hope you learned more about the physics of catapults.